In this video we're going to be looking at the difference between analog signals and digital signals. And to highlight this, what I'm going to do is I'm going to show you an example of an analog one first. Alright, so in this case I've got VCC and ground, and I've got a variable resistor. The voltage here, output voltage, is a function of the variable resistor voltage position, would do something approximately equal to this, where on this axis we have voltage and on this axis we have pot position. But what we note is that even if we zoom in on this curve, we would still see a smooth continuous line. In other words, an analog signal is a continuous signal. There's no discrete steps in it. Alright, that's quite fundamental. So analog, like the voltage here, okay, and I'll just write this up here. Analog. Other things which are analog, things like temperature, light level, pressure, and many other of the fundamental quantities that we want to be able to measure are analog quantities. They are continuous. Alright? They don't do things like this, just don't exist between 2 points. They don't suddenly jump between 2 points. Alright? So they're smooth, continuous. They don't have to be straight lines. Alright? A continuous signal may also be a sine wave, and that's fine. Okay? That is also an analog signal. But I'm looking specifically at ones that do not have these sharp changes or breaks, discontinuities within them. So let's have a look then at what a digital signal would look like instead. And easiest analogy is a switch. Okay, VCC, V out. Alright, the switch goes on at some time t, voltage, and the voltage goes up when you close the switch. So we have two, in this case, discrete voltage steps. So, noting that word, discrete voltage steps, or just that word discrete in general. Okay, we have this value and we have this value. It does not exist between those. Right? It's not possible to get any other voltage between those, assuming an ideal theoretical switch. Right? This is a property of discrete signals. Let's take another example. Alright, let's say we've got a voltage divider ladder like this, and we've got a switch that allows us to switch between those positions. Alright, so this would be like a rotary switch turning between, for example, the input sources, or just in this case, between different voltages. Right, so at this point here it becomes V out. Once again, we have a whole series of discrete steps. So output voltage, this time versus switch position. Okay, we've got 4 switch positions, which gives us 4 discrete values of voltage output. 0, 1, 2, 3, or 1 to 4. Alright, so once again noting discrete voltage levels, alright, with discontinuities between them. In reality, that bit doesn't even exist. Right? The line there doesn't even exist. They only look like that. Okay, hence you can see the discontinuity between them. So, analog, continuous signals, even if you zoom in, on that little bit there, it would still be continuous. Okay, things like temperature, light level, pressure, voltage, current are all continuous quantities versus digital, which has discrete steps like words like switching, numbers, binary, are all discrete or digital terminology. When we look at representing digital values within a circuit, normally, although I've said this is digital up here, normally we're interested between 0 and 1. Those are our normal digital quantities. Alright, so the 0 state and the 1 state. Normally, this would be, for example, switch open, switch closed. That's my switch. That's the 0 position. That's the 1 position. Alright, other names that we could say for this: logic low, or logic high, or logic 0, logic 1. You can also use terms like false or true. Or we could use voltage levels, 0 volts, or for example 5 volts, 3.3, whatever happens to be the VCC level in the circuit. So depending on, I'll just draw arrows over here, this one and this one. Just remember, this is what we call positive logic, but this is the normal one that we're going to be using. Right, there's lots of names to represent the same condition. When the switch is open, logic low. The value here that we're interested in is low. Logic 0, false, 0 volts. When the switch is closed, obviously if we've got VCC here and V out here, V out equals VCC equals high, true, 1. Those are all names associated with this. Right, so with digital systems, primarily we're interested in whether it is a 0 or a 1. Those are our two conditions. When we look at whether or not we say it is equal to a 1 or a 0, we don't say it has to be these voltages. That would be unrealistic. So what we actually do, and I'm going to give you the TTL, or transistor logic level values, is there actually a range of values which are considered to be on and off voltages. And it varies depending on whether you are using it as an input or using it as an output. So I'm just writing these ones down, and 0 volts. So this is our logic 1, logic 1, logic 0, and logic 0. Unusable region, and this is a TTL output, and this is a TTL input. So what this basically states is that if you're going to supply a true condition, or logic 1 or high, then your output voltage for your circuit must fall within this range. Alright, so 3.3 volts would be a logic 1. 4.9 volts would be a logic 1. And similarly, false or logic 0 or low corresponds to any voltage 0.4 volts and below. Right, so there's a range of voltages that you can output, and that takes into account different operating conditions, different components, different tolerances within the circuit. Right, so it gives you quite a wide operating region. Also means we don't have to go right up to 5 volts. We could also operate at 3.3 and still work correctly with this system. Note that for inputs, the range is slightly different. Right, for inputs, noting it's lower than the output, and the reason being that if there's a small voltage drop between the TTL output, so let's just draw it. Here's our TTL digital device with our output. Let's say it's at 2.7 volts. There's a small line resistance, okay, and it reaches here at 2.3 volts into this device. Okay, because of this small resistance in the connection pathway. Alright, if it used the same voltage, 2.7 going out, and expected 2.7, that would be in the unusable region. But because the input is a little bit more relaxed, 2.3 is greater than 2, so it's equal to a logic 1. Alright, so we see there's a small difference here, and correspondingly there might be a slightly there's a slightly larger range, just in case, in the sense that if we do output, let's say at 0.4 volts, and there's a whole lot of interference and noise in the line, so by the time it reaches the input device, it's actually gone up to 0.6 volts, alright, because we've got some noise on the signal. That's fine, we're still below the logic 0 threshold. So, noting that we have thresholds and usable regions to operate these devices in. Alright, so quick summary, analog versus digital. Analog, right, continuous is the key word. Alright, so a continuous signal, no matter how much you zoom into it, examples are like a pot here, or some physical quantities that we'd measure. Right, doesn't have to be straight lines, can be any sinusoidal, triangular, and all those sorts of things. Those are fine. Right, those are continuous signals. Discrete signals or digital signals are ones that have discrete values or fixed values. All right, they don't exist continuously between those values. Okay, so it could be just 0 and 1 or 0 and VCC, or it could be multiple values. But normally, we're going to be thinking of digital, we're going to be thinking of just zeros and ones. Just on and off are the two main states. Lots of ways that we can say that. Okay, on and off, switch, okay, I probably should write those in here. Off and on there. Switch closed is on, high, logic 1, true, or a high voltage, and corresponding for the off position. And noting that there is a tolerance around that. So a logic 1 would fit into, let's say, the output of 3.3 volts. Okay, or a logic 1 would also fall into the input of 2.5 volts, if we're looking at it from an in point of view. So different ways you can look at the same signal, just giving a little bit of operational tolerance.